Okay, today's lesson on related rates involves problems where we are going to be substituting to get fewer variables in the problem. So let's go ahead and look directly at this example. An inverted cone has a height of 9 centimeters and a diameter of 6 centimeters. It is leaking water at the rate of 1 cubic centimeter per minute. Find the rate at which the water level is dropping when h equals 3 centimeters. So inside of this cone, there's water, and the water also is in the shape of a cone. They give us the information that the height of the cone is 9 centimeters and the diameter is 6 centimeters. They give us our dV/dt. I can tell it's dV/dt by looking at the units, cubic centimeters per minute. So our dV/dt is a negative 1 cubic centimeters per minute. Since water is leaking, the cone of water is going to be having a volume that's decreasing. Find the rate at which the water level is dropping. So if you imagine the water level dropping, that would be a rate of change of height. So dH/dt is what they're wanting us to find when h is equal to 3. Okay, let's take a look at this volume formula for a cone that they give us over here on the left. If we were to differentiate that as is with respect to t, we would have to use product rule because we have both an r and an h as variables. What's more, after we take our derivative, we would have a dr dt and a dH dt that we would need to plug in. We weren't given a dr dt. We were only given a dH dt. So we'd have a lot of trouble finishing this problem because we're just missing some information that we need to have. So what we're going to do instead is we're going to go into this volume formula. We're going to substitute something in place of r so that our entire equation is only in terms of h. Why h? Well, let's look at this given information here. We want to find dH dt and we're given a height. So r really isn't that important in the problem. We're going to substitute, get rid of the r in the equation and only deal with v's and h's. So do you see how they gave us that the diameter is 6 and the height is 9? So if we go even smaller on this cone and find its radius, the radius of the cone is going to equal 3 centimeters. So what I hope you notice is that the height of the cone is 3 times bigger than the radius. So since the radius is 3 and the height is 9, the height is 3 times bigger than the radius. Or if we divide that height by 3, we're given the radius. That relationship between the height and the radius stays true no matter how much water is left in the cone. So the height of the water is always 3 times the radius of the water. Okay, so let's go to our volume formula on the left here, and in place of r, we're going to input that h over 3. Now we have this only in terms of h. But what we're going to do next is simplify it so we don't have to use product rule. So I'm going to square what's in the parentheses, and that gives me h squared over 9 times h here. Let's go ahead and combine on the right-hand side. So we have that 1/3 times the 9 gives 1 over 27 pi h cubed. So we've done no calculus so far. We've only done geometry and algebra to rewrite our volume formula for this particular cone, so it's only in terms of h. I'm going to move over here to the right-hand side where we have more room, and we're going to differentiate. So now we're going to take the derivative with respect to t. On the right, we don't need product rule since that 1 over 27 pi is all the coefficient. So applying the power rule, we get 3 over 27, which reduces to 1/9. pi h squared dh dt. Okay, let's take a look at what we have and what we need in order to answer the question. So they give us a dv dt, they give us an h, and our dh dt is our unknown. Perfect. So plugging in, we get -1 centimeters cubed per minute. And that's equal to 1/9 pi. And then we have h squared and then dh dt. In place of h, we're going to plug in that 3 centimeters. So that gives us -1 centimeters cubed per minute. On the right-hand side, we have that 1/9 pi, and then 9 centimeters squared dh dt. The 9's on the right cancel, so we have -1. And let's go ahead and cancel some of the units. We can divide a centimeter squared out of both sides, so that leaves us with -1 centimeters per minute equals pi dh dt. So dh dt is just equal to -1 over pi centimeter per minute. So that's our answer. Let's answer in a complete sentence. The water level is dropping 1 over pi centimeters per minute. So when we answer in a complete sentence, the main thing I wanted you to notice there is we can get rid of the negative, since the negative implies that our rate is getting smaller, and so does the word dropping. We don't need the word dropping and the negative sign. Okay, the next example says gravel is poured onto a conical pile at 3 cubic meters per minute. So because cubic meters are units for volume, this is dv dt. And since gravel is being added to the pile, dv dt is positive since the volume would be increasing. The diameter of the pile is always equal to the height. At what rate is the radius changing? So dr dt is our unknown. At the instant that the radius is 8 meters. So on this example, it looks like r is the variable that's most important. So we're going to take our volume equals 1/3 pi r squared h, the volume formula for cone, and we're going to substitute in place of h some expression with r so that we can get our volume only in terms of r. So they did tell us that the diameter is equal to the height. So as you know, the radius is half of the diameter, so 2 radii equals the diameter, so 2 radii equals the height. So I can go back here in place of the height and input 2r. So before I differentiate, I want to clean this up a little bit. So actually I'm going to multiply the 2 times the 1/3. That gives me a coefficient of 2/3, pi, and then r cubed. So now that I've cleaned up the volume formula for this particular cone, I can go ahead and differentiate with respect to t. dv dt equals, let's go ahead and use the power rule so that 3 comes to the front. And as you know, 3 times 2/3, those 3's are going to reduce, so that equals 2. So our coefficient is 2 pi r squared dr dt. Since we differentiated the r, we multiply by dr dt. Okay, so dv dt in this problem is 3 meters squared per minute. We have on the right-hand side 2 pi and then r squared. dr dt is what we're trying to solve for. Okay, so I think we'll just simplify the right-hand side a little bit, and then we'll divide. So in the parentheses, we're squaring that 8. So 8 squared is 64, and then times the 2 in front gives us 128 pi meters squared dr dt. So we can cancel out, oops, I'm sorry, on the left-hand side is supposed to be 3 meters cubed per minute. Let's change that. Okay, let's cancel out a meter squared out of both sides, and that gets rid of the cubed on that meters. And so to get dr/dt by itself, I'm just going to divide both sides by that 128 pi. So we get 3 over 128 pi meters per minute. Make sure the pi stays in the denominator. Okay, so our pile is growing, so dr/dt should be positive. And meters per minute, those are appropriate units for the rate of change of a radius. Since a radius is in one dimension, meters per minute are appropriate units for that rate of change. A spherical weather balloon is losing air at 2 cubic feet per minute. So again, we are given dv/dt in this problem. It's negative since it's losing volume. At what rate is the radius changing? So again, they're asking us for dr/dt. At the instant that the volume is 256 pi over 3 feet cubed. Okay, so we have our volume formula. Volume equals 4/3 pi r cubed. So volume is changing in this problem and radius is also changing. So nothing in that equation is going to stay constant. So I'm just ready to differentiate. So our derivative dv/dt. Let's apply the power rule, bring that 3 to the front. And so again, we're going to have 3 times 4/3. So the 3's cancel. And so we have 4 pi r squared dr/dt. Okay, let's take stock of what we need and what we have. So we have a dv/dt. We're trying to find dr/dt. I put that question mark by the wrong thing. We're trying to find dr/dt. So that's our question mark. And we don't know r, but we can find r. So they've given us the volume of the sphere. So what we're going to do is we're going to set the volume formula for the sphere equal to the volume of the sphere. So 4/3 pi r cubed, we set that equal to the volume, including the feet cubed. Okay, so we can cancel a pi out of both sides. We can cancel a 3 out of both sides. So we're left with 4r cubed equals 256 feet cubed. Dividing both sides by 4. 4 goes into 25 6 times, and then we have 1 left over. And then 4 goes into 16 4 times. So we get 64 feet cubed, and then let's cube root both sides, so the radius comes out to be 4 feet. So we are able to then just use information that we had and solve for r. So we can go ahead and plug in and then find our dr/dt. So dv/dt is that -2 cubic feet per minute, and that's going to equal 4 pi. The radius is 4 feet. Let's square that and then times dr/dt. Okay, on the right-hand side, we have 4 squared, which is 64. 4 squared is 16. 16 times another 4 is 64. So our coefficient on the right is 64 pi feet squared dr/dt. So let's divide a feet squared out of both sides, and that's going to take care of that cubed on the feet. Then we have, we're going to divide both sides by that 64 pi, so we get -2 over 64 pi feet per minute. So since the weather balloon is losing volume, it is going to have a decreasing radius, so our sign should be negative, and again, feet per minute are appropriate units for the rate of change of a radius.